Hi everyone, this is the last case of this project. In this video, we will solve a cantilever beam with a spring support. We will solve this problem using a special element called zero length element of OpenSees. These zero length elements are mainly developed to model the effects of support conditions. For example, boundary conditions such as rigid fixed supports do not allow any translation or rotation like this one. Hence, we put 0 for translation and rotation at fixed supports. Another interesting scenario is pinned support or hinge support. It resists the translation, but it cannot resist the rotation. Hence, we put 0 for translation DOFs and let the member rotate to any degree. Similarly, in roller support, only vertical displacement is restrained and all other translation and rotation DOFs are allowed. Hence, we put 0 only for the vertical translation DOF and let the member move or rotate in other DOFs. But this is not the case with this kind of spring supports. These comes under a category called flexible supports because these supports offer only a partial resistance. Hence we cannot put 0 and in fact we don't know what value to put here as stiffness for this kind of supports. This has to be evaluated using material constitutive relationship. The problem we considered in this case is taken from R.C. Hibbeler. It is an unsolved problem. These are the moment of inertia and Young's modulus of this particular cantilever column. This column has, sorry, it's not a column, it's a beam. This beam is of width 5 mm and it's 200 mm long and its thickness is 10 mm. Width is something perpendicular to this screen. A load of 50 Newton is applied at the a load of 50 Newton is applied at this end B, and the analytical displacements that we have observed is 1.5 mm downward. This is evaluated using virtual load method. We use the same libraries that we used in the previous two cases. Let's install them and import them using the names as you need or as you like it. Here we define the geometric and material properties of this proper cantilever. We consider two nodes. First one to model the node A and second one to model this node B. As it is a 2D model but with a 3D wave system, only X and Y coordinates are enough. And I have specified here the length, width, depth, cross-sectional area, Young's modulus, and the stiffness of the spring is given as 2 Newton per mm. This is already given in the problem. Since it is a linear problem, we can take it as constant, but if it is a nonlinear problem, this has to be evaluated using the nonlinear constitutive relationships. Imagine zero length element as some sort of spring actually. It has two nodes, but those two nodes exist at the same location. For that purpose, we created an extra node, node number 3, exactly at the location where node number 2 exists. And the element that connects these two nodes, 2 and 3, the zero length element, is modeled using an elastic material which takes the stiffness value as given in the problem description. This is how we define a zero length element. It has a tag. Tag is a number that we give to this element. It's some sort of an element number. We specify the material using material tag, that is the elastic material with stiffness K and one material number 1, and a direction tag. Direction refers to the direction in which this zero length element deforms. Here I specified it as 2. It means 1, 2 and 3 are the translation along XYZ axis and 4, 5, 6 are the rotation about local XYZ axis. I have given 2, which means our beam, which means our zero length element deforms only in the Y direction, means vertical direction, and all other deformations in the horizontal and rotation are restrained. We specify fixed boundary conditions at nodes 1 and 3. At these nodes, all the displacements and rotations are completely restrained. And we apply an external load of 50 Newton, which is stored in this V load using a linear time series and pattern commands. This is how our beam looks actually. Node 1 is completely fixed and node 2 and 3 exists at the same location, and node 3 is completely restrained and node 2 is supported on this spring with flexible stiffness, and 1 refers to the element number 1. In this model we considered only one element. The analysis settings that we used here are somewhat similar to the ones that we used in the load control analysis that we performed in case 2. After performing the load control analysis, let's see what we have got from the results. So using node disp command, we extract the displacements at node 2, x and y directions, that is 1 and 2 directions, and third direction is rotation here at node 2, and that value we store it in theta z at node 2, and when we print these values, we have got its zero displacement in the x direction and a negative 1.5 mm in the downward direction and some rotation value, and the analytical value that we have got is 1.503, which is acting downward and which is evaluated using the virtual work or unit load method. When we compare these values, uh, what we have got is almost equals to 1. So it means the analysis value is almost matching with the analytical value. This is how the beam deforms, and this kind of deformation diagram can be found using this plot deform command of this OpenSees visualization library. And these are the nodal reactions and support moment reaction evaluated using regular equilibrium equations. And when we extract them from the OpenSys simulation, what we have got are Rx1 is 00, Ry1 means the vertical reaction at node 1 is 46.999, which is almost equals to 47, and the rotation is the moment is 9398 Newton millimeter. So it's a very high value because the beam is quite long, 200 mm, and the load is acting at the extreme end. When we look at the equilibrium values and the values that we have got from the OpenSys, if you look at the moment ratio is almost equals to 1 and the vertical force ratio is also almost equals to 1. It means our analysis results are exactly matching with the analytical values. This is the way we perform validations before performing our finite element simulations. Validation is a very important step actually. We have to perform it against a known result. The known result can be an experimental data or an analytical solution. In project 1, we have performed a kind of validation using the experimental data, and in this project, we are performing the validations against a known solution, that is analytical solution. After validating your finite element model against a known solution, you are good to perform parametric studies on the similar geometry. If you have any questions or need any help, you are always welcome to post them in the course discussion forum, and also you can always email them to elastropy@gmail.com. Happy learning. Thank you.